Let's take a look at a couple of applications, one involving bacteria in the human bladder, and the other involving the decay rate of a copy machine. So in this problem, a scientist studied the bacteria E. coli commonly found in the human bladder. And suppose that in their study, 3,000 of the bacteria are present at the beginning of the study. That's when time is 0. That's where this 3,000 comes from. Then, t minutes later, the number of bacteria that are present can be approximated by this equation. T minutes later. So 10 minutes, 20 minutes, 30 minutes, 40 minutes, 60 minutes, the bacteria are growing in the human bladder. So I'm going to take this formula, which is 3,000 times 2. In the first case, I'm going to put a 10 in here, and 10 divided by 20 is a half. So 3,000 times 2 to the 1/2 power, which means the square root of 2. But I'm going to take my calculator and do this. So I'm going to go second quit, and 3,000 times 2 to the, for me I got to put it in parentheses, 1/2 power. I know it's the square root of 2. 4,242.6. I might call it 4243, I think is what I'm going to call this. 4243. Let's do the next one. And then we're going to let the calculator do the work for us. In the next one, I'm going to put in for n a 20. And so, I'm sorry, for t, a value of 20. And 20 divided by 20 is 1. So I have 3,000 times 2 to the first power, or 3,000 times 2, is 6,000 bacteria. Now, remember, we started with 3,000. So it looks like every 20 minutes it will double. So let's go to the 40. So 3,000 times 2 to the 40 divided by 20, which is 2 squared, 2 to the second power, which is 4, and 3,000 times 4 is 12,000. And so probably I'm going to find that this is going to be 24,000. Let's let the calculator do all the work for us. So let's be reminded of the fact that it can create a table for us. So we'll go here, and we'll clear these formulas, and we'll put in 3,000 times 2 to the x divided by 20 power in parentheses. Then we're going to tell the calculator that we'd like to have it set up a table of values where it starts with the number 10 and goes in increments of 10, mostly because I got to go 10, 20, 30, 40, and then right here I have a difference of 20. But I'm going to start it at 10 and have it go in increments of 10, and now I'll go second and the graph key, or the table, to get the numbers we'd been getting anyway. Here's the 12,000 for 40, here's the 24,000 for 60. The only one I don't have written down is 30. It's 8485. So this is a doubling situation, and it's doubling every 20 minutes. And I hope to now graph this data on the curve below here. So you're going to have to imagine the data. I might bring it down, is what I might do here in a minute. But what I really need you to do is I need you to label the x and the y-axis appropriately. I'm going to go ahead and bring the data down real quickly. 10, 42, 43, 20 was 6,000. I remember that 40 was 12,000. I remember that 60 was 24,000. And 30 minutes was 8485. So I want you to graph this with time on the x-axis in minutes. So you've got to tell me what the x-axis represents, and you got to tell me the units that are represented. And then I want you to come up here and put that the y-axis represents the number of bacteria. And I'm going to go ahead and keep this in thousands. So I'm going to break this, I want to kind of stretch my graph out, and I got to go from 0 to 60 here on the x-axis. So I think I'm going to, every 3 marks, I'm going to put 10 minutes. I think that'll be good. So 10 minutes, 20 minutes, 30, 40, 50, 60, not bad. And then I've got to go from 0 to 24,000 up here. So I think I determined that it'd be nice to go in increments of 4,000, 8,000, 12,000, because I'll be able to get to 24,000 this way. So this would be 16,000, and then here would be 20,000, and then finally right here 24,000 bacteria. So when x is 10, I go to the right 10, and I go up 4,243, probably about right there. When x is 20, I go up to 6,000, which is about right here. It's between the 4,000 and the 8,000. When x is 30, I'm above 8,000, getting halfway between 8 and 9,000. At 40, I'm at 12,000. It's a little hard to see this exponential growth curve until you get this last point. So you go to 60 and 24,000. Remember that when we started this study, we had 3,000 bacteria cells. So at time 0, we had 3,000. And I wish for you to connect the dots and show the exponential growth of this E. coli, and here's where it's really starting to take off. And we probably have a problem if we have some E. coli in the human bladder, and we're probably going to need an antibiotic. Let's go on to the next one. A photocopier is purchased for $5,200. $5,200. Its value each year is 80% of the value from the preceding year. So you see the 0.8? That means you keep 80% of its value and you lose 20%. But I want you to recognize that this is a number between 0 and 1. And a number between 0 and 1 is a decay situation. A minute ago with the bacteria, we had the number 2, and that was a growth situation. So I could put this equation into my calculator. So I could go here and put in y equals 5,200 times 0.8 to the x power, and then I think I have to get rid of a few things. I think that's it. I could start my table at year 0, because my table's going to start at year 0. Remember, anything to the 0 power is 1. So 0.8 to the 0 power would be 1, and 1 times 5,200 should be 5,200 right here. So the value of the copier right at the start of its purchase should be 5,200. I'll go in increments of 1 though, here. And then I'm going to go second in the graph key to see that when I bought it, it was worth $5,200. But at the end of year 1, it had lost 20% of its value, or it was now worth 80% of its value. And so I'm going to go ahead and put these values into my table. And I want to graph the exponential decay curve for this copy machine. It's worth hardly anything at year 10, and companies have to depreciate their equipment, and this may be how this particular piece of equipment is depreciated on their balance sheet. So again, I'm going to go ahead and say time over here. I've got year 0, 1, 2, 3, I think 5, and then 10. And the data came out to be $5,200 value, dropped to be $4,160, $3,328. Really a good application because accountants have to do this. They have to depreciate. Oops, I think I've lost a number. 1, 2, 3, 5 is, cannot see what I've lost. Oh, there was no 3. That's what it was. So 5 was 1703.90. In year 10, it was worth $558.35. So if you're showing this to the manager, you're an accountant and presenting this, you may have to show the decay rate of this copy machine in the form of a graph. So on the x-axis, I'm going to represent time in years. for the value of this copy machine, and on the y-axis I'm going to put value in dollars. You know, it could be in yen or, you know, whatever monetary value if it's in a different country. And then on here on the x-axis, I want to kind of spread this out a little bit, so I'm going to go year 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe I'll go in increments of, I'll just write down the 2, 4, 6, and 8. You don't have to write them all down, but they just have to be equal increments. And I have to go from you know, $500 up to $5,200. So I'm going to go 1,000, 2,000, 3,000, 4,000, 5,000. To try to use up some space to see the actual decay, if you draw your graph really small and you don't separate the tick marks on the axes, you will not see the data very well. So at time 0, it was worth $5,200, just below $5,250, because these are 250, 500, 750, and 1,000. At year 1, it's worth 4,160, probably about right there. Year 2, it's worth 3,000. This is 3,250, 500, so let's go about right there. In year 5, it's only worth, here's 1,000, 1,250, 1,500. Here's 1,750, so right below that. And then finally, in year 10, it's only worth about $558. So we can really see the exponential quick decay, little bit, and over this 5-year period, not much decaying as it goes on and runs out its life, and probably at some point doesn't have any value. This is ends our study of exponential functions and growth and decay rates. We're going to introduce logarithmic functions in our next segment.